Okay, so I'll be talking about how to brew your own alcohol, but it's not brewing your own alcohol because we are turning alkenes into alcohols. It's not just an A-push reference. Okay, so let's start. Okay, so suppose we're in organic synthesis 101, and so I have this molecule. This is called isobutene. I want to synthesize tertiary butanol from isobutene. So someone can tell me what I'm gonna do. So like,
this is very much like our homework.
Okay, so just briefly tell like what reagents will we use.
You're going to need some proton and water. Yeah.
Exactly. Exactly. Protons and water. Very good. So different problem. Now you have this molecule, which is called I'm gonna name it right. I'm gonna name it right on the spot. 3-methyl 1-butane. Sorry, butene. Okay. So I still want to add an alcohol group. And do you still think I can like just add water and protons and it will just do this?
No, because
Why?
of carbon-cation rearrangement.
Yay. So carbon-cation rearrangement is something we don't like to see. Well, because this carbon is just a secondary carbon-cation, want to make it a tertiary. So so there's a hydride shift. And then our lovely water just adds onto this carbon, which is not what we want. So what are we gonna do in this case? Where, as to quote Ms. Jones, we will force the alkene out of its comfort zone by introducing this method called oxymercuration-demercuration. In Chinese is 阳汞化、去汞化. So we are using this thing called mercuric acetate, and okay, so it dissociates into this mercuric cation, which is very electrophilic, and so basically it's a two-step process. So first step, you will add this mercuric cation onto your alkene, and then along with a nucleophile. Most of the time it's water, but it can be something else. And then to remove the mercury, we'll use NaBH4, which everyone loves. So how is this possible? So first of all, the double bond will attack the mercury cation and then form this cyclic intermediate. You will see that this cyclic intermediate looks very familiar to the bromonium ion that Helen introduced last time. So this is called a mercurinium ion, which, well, is obviously named in the same way. And then, so a nucleophile can attack this slightly more like electropositive carbon, which is the more substituted carbon. And then the nucleophile will add onto this carbon, and then the other place will just be this mercury stuff. So obviously this is a Markovnikov addition, and as you can see, there is no carbocation form. Like even in this intermediate, the carbocation is like quickly neutralized by the lone pair on the mercury. So there's no carbocation, there's no rearrangement. That's so nice. And to remove the mercury, we just need NaBH4, sodium borohydride, a really strong reducing agent. And then we can get a hydrogen onto there. So by these two steps, we have at 94% yield of just this product, there is no rearrangement observed. That's so nice. We love this. Like, because
yes, we all love sodium borohydride.
Yeah, we all love sodium borohydride, yeah. And because like in organic synthesis, organic chemists, what they really hate is they really hate like side reactions. Side reactions will include like these kind of things, carbocation rearrangements. So this method was developed actually many years ago to like eliminate the possibility of a carbocation rearrangement. So this is a very useful thing in organic synthesis. Okay, big question here: Is this process syn or anti-addition? Anyone want to take a guess?
Can you show that reaction again? Okay.
So do you think the nucleophile and the hydrogen will be on the same side or opposite sides of the double bond?
Very tricky question, Jack.
It should be anti, right?
Why is that?
Don't ask me.
But you have an idea. You can say you guessed it. It's fine.
Yeah, I like the way Jack showed the second step, right, by using a dash line. So which means there's no carbocation produced as an intermediate. But this can clearly show why the nucleophile prefer to attack here, because when it carries more positive charge, it's more stable because it's more substituted, right? But it's not breaking first and then the nucleophile go later. It's kind of happening at the same time. But definitely you still keep the ring structure, which is quite similar to the bromination, right? You also have the a similar stuff. This is called Mercuranian. That one is called brominium.
Yeah, like also similar ones include the protonated epoxide ion, but we don't cover that. So, in fact, Helen got it right. It is an anti-addition. And to explain why it is an anti-addition, it's actually very similar to when you deal with the bromonium ion. So we can imagine there's an arbitrary plane. So in this drawing, all the black stuff are in the plane, and the blue parts are above the plane, the red parts are below the plane. So you can see here that the mercury, because mercury is a very big atom, so the mercury will take up a lot of space above the plane, above the double bond. So if the nucleophile wants to attack it here, it's gonna have a bad time, because well sometimes the nucleophiles are like quite big, and then it cannot fit itself into this hole here. So what it can do is it can only attack from the other side, which is not blocked at all. So it will create an anti-addition because the mercury ion is on this side, and then the nucleophile will attack from the other side. And then in the process that removes the mercury, there's no conformational change, so it stays an anti-addition. So yay, we got. So yeah, we don't have carbocation rearrangements in oxymercuration-demercuration. It's nice. So suppose we are now in organic synthesis 102. Before, in organic synthesis 101, we wanted to get tertiary butanol from isobutene. So what if I want to get isobutanol, which is the OH adding onto this less substituted carbon? Well, that would not be possible, right? If you only add water and like protons, because there's a thing called Markovnikov's rule, which states that the intermediate, the carbocation intermediate will always want to bind, will always want to stay in a more stable position. In this case, the tertiary carbocation position. So you don't get this product. And now we want to make Markovnikov set because we're gonna do an anti-Markovnikov addition. So introducing hydroboration-oxidation is also a two-step mechanism. And the key thing we're using here is boron, BH3. So BH3 is, well, it's not a really like healthy thing. And also BH3, it's like the boron is really electron deficient because like imagine BH3 as a primary carbocation. Like primary carbocation is CH3 plus, and BH3 is like almost the same with the like CH3 plus.
Actually, they are isoelectronic species, right?
Yeah,
CH3 plus
yeah.
and BH3.
Yeah, so you can imagine that BH3 it has a empty p orbital. So in this case, actually the hydrogen is carrying most of the electron density, and boron is really electron deficient. So actually in the solution, we'll see the BH3, they will dimerize into this thing called diboron, which is B2H6. And well, this is not a normal bond you will see, hydrogen forming two bonds. Well, it happens. It's called the 三中心两电子键. And then I don't think we'll cover this, but just to throw it out there, like B2H6, the diboron is less reactive than BH3. Well, because the like electron density of the hydrogen is kind of shared. So like when we use boron in hydroboration process, well, we usually couple it with a solvent such as THF, which is tetrahydrofuran. In Chinese, is 四氢呋喃. Looks like this. Want to guess why? Like, why is it important to have a solvent such as THF if you want to have BH3?
To prevent dimerization.
Exactly, because the lone pairs on the oxygen will donate electron density to the boron, and then the boron will be kinda electronegative, but the BH bond is still like the electron density is still like polarized to the H side, to the hydrogen side. So this does not affect the actual reaction. So it is also two steps. First step is just using BH3 in THF. And then the second step is called oxidation. We will use hydrogen peroxide and a base. The base is just to deprotonate the hydrogen peroxide. So we usually use sodium hydroxide. Because the OH minus is a stronger base than the hydro peroxide thing. Well, so how exactly does this achieve the anti-M rule addition? So if we think about what M rule is about, it's like when the double bond attacks this compound, the double bond will like it will first form bond with the electropositive or the electrophilic part. The other part will just like add onto the carbocation. But in this case, like in normal cases, the hydrogen is the electrophilic part. For example, in HCl and H2O. But in this case, in BH3, the boron is actually the electropositive or the electrophilic part. So the less substitute position will form bond with the boron, and then the hydrogen can migrate to this more stable carbocation here. So in this case, we have successfully put the hydrogen on the more substituted position. So this is how, like, basically how anti-M rule works. Because when the hydrogen is on the more substituted position, you just cannot rip it off anymore. You can change the BH2 to whatever you like. And interestingly, one borane molecule is able to react with 3 of these double bonds to form a trialkyl borane. I think that's what we call it. Yeah, trialkyl borane. And I'll use R to save some drawing. Okay, so now we have this trialkyl borane, which is the hydroboration part. So what next? The next is the oxidation part. I think we did a question related to this before. I think that was on arrow pushing mechanism. But now I will more systematically introduce this process. So when the hydrogen peroxide is deprotonated, this oxygen is like nucleophilic. It will attack the boron and then form this bond. And then because the OO bond is kind of not stable enough, then this R group will migrate. The R group will migrate to the oxygen and then kick off an OH group. So now we have an OR, alkoxyl group, instead of just an R group. So we can also repeat this process using more hydrogen peroxide to achieve this thing. So all of the 3 R groups have been substituted with OR groups, which are which in this case is called a trialkoxy borane. And then lastly, we want to get an alcohol, right? So now we have an oxygen on there, so we just have to kick it off. Basically, you still have an OH group, like OH minus, to attack the boron. Because the OR group is a better leaving group than the OH group. So if we add the OH onto the boron, it will tend to substitute a OR group for the OH group. So we have an alkoxy ion, and it can be protonated by water to form ROH, which is the alcohol that we ultimately want. And surprisingly, in this super complicated process, it the conformation of this bond has not changed. It's still OH group on here. And so we've successfully made my company called SAD because, well, we're not following his rules anymore. For example, in this case, we have hexene. Hexene using hydroboration-oxidation, we get 90% yield with one hexanol, when normally you only get 2 hexanol. So nice. Okay. Also, still the big question is this reaction syn or anti? I think I want to nominate Vincent to answer this question.
I don't want to be voluntold.
It's fun. It's mandatory fun, Vincent. Take a guess. I can show you this thing.
This is a little bit misleading.
No. Is it?
Okay, well, wait.
It's nice.
Come on, you have a 50% chance of getting it right. It's not like a test. Just have a guess.
Yeah, it's not like the debate. You don't have to be responsible for your answer.
Anti?
Well, since you got the wrong side of the coin, it's actually syn. So we still use arbitrary plane to explain this. So basically, well, BH2 when the carbon boron bond forms, it can form at either face of the double bond. So let's suppose it's the upper face. And then, well, the hydrogen wants to migrate to this carbon. Well, the hydrogen have two choices. It can either migrate to this big lobe of no electron density that is really close, or it can migrate to the big empty electron density lobe that is very far. So obviously it will choose this one because it's closer. But like you cannot really ask a hydrogen to go all the way around a double bond just to form like donate its electron density to this lobe. So the H and the BH2, they will be on the same side of the double bond. And surprisingly, in this complicated process, like adding, kicking off groups, the conformation of this bond did not change. So it's basically like things to do with the boron. It's not things to do with how the group is connected to this carbon, and there's no carbon bond rotation or anything. So this bond stays the same and creates a syn addition. Okay, that's nice. One more thing to know, because I saw this question in the lecture notes. So someone tell me what's going on here. Let's see. William can answer this question, right?
So basically, instead of hydrogen, you use deuterium on the like boring. So when the hydride is shifted, it instead shifts like a deuterium instead of like H plus, H minus.
Yep. So basically, deuterium, or D, is just a version of hydrogen that has one more neutron. So basically, deuterium is like used when you want to do like isotope tracing in organic synthesis. So what we're looking here is that we're using BD3 instead of BH3, and if we remember here, the one of the hydrogen from the boron is actually ends up on the final product, the alcohol. So in this case, the deuterium will be here, and that's an important thing to know. Otherwise, you cannot do your homework. I think, yeah, that's about it. Just these two reactions telling you how to brew your own alcohol in 2 steps. So they are like very special in the way that they don't follow the usual rules. Like if you just use for example HCl or like plain reagents or like acid-catalyzed hydrations, you have to follow like Markovnikov rules or like carbocation rearrangements. But these two reactions that I just introduced, they don't follow these rules. So if we want to actually synthesize something like this, these two processes will be extremely helpful. Any questions so far? No? Good.
I have a quick question about hydroboration.
Yes.
Actually, oxymercuration-demercuration.
Yeah. Go
yes,
ahead.
it is indeed anti-addition, but I thought like the demercuration step involves a radical addition. So why would it be like? Are you sure that NaBH4 will not change the conformation?
Well, since it's a radical process, it's like everything is by chance.
Yeah.
But still, I don't think so. Like, how exactly would you expect it to change the conformation?
I think it'll become a racemic.
Like, is okay. So you're saying you think you think the single bond will rotate because this is just one carbon. It's not nucleophilic substitution in Yang. There's no like this kind of wiggly stuff. Like if you want to change the conformation of that carbon, the only way you can do is to rotate the single bond.
What?
Well, theoretically, like I'm not as a good organic chemist as you are, but I think like it's, but like even if you form a radical,
Radicals are sp2, so you can have like either conformation.
It's
Because,
actually
like,
between
the-
sp2 and sp3.
Yeah,
So,
maybe
like,
later, yeah, you can show the mechanism of the demercuration step,
I can't find it online.
and then we can have
like because it's a radical process. Like normally we just expect like negative hydrogen just attacks this mercury and pushes it off, and
But then
it
that's
gets-
gonna reverse the conformation.
I never heard about
or it's gonna be a racemic mixture. It's entirely possible. Like, but normally I don't know. That's probably
Yeah, Google says it's anti too, but I don't understand why.
Yeah, you can find the mechanism for the second step, and then we can talk based on that. Otherwise, without knowing the exact mechanism, it's kind of a invalid argument.
Okay.
Okay, so Yang has been banned from asking any more questions. Okay, so if no question, I'll just give you the reading quiz. No, so as I just said, my part actually includes a summary of everything that we just learned. Not just what I introduced, also what Vincent and Helen and William introduced. So I guess it's just like I just like condensed it down to this small chart here. I think that's all we like need to know. Okay, so I think I don't know, Dr. So like Dr. Chen, if you agree to this, I think we can like one person do one row. And then
Oh yeah, definitely. This is a good idea. We can all type. Let me see. Hey? Oh, okay, it works. It works. But it seems like I cannot change.
You can like delete it and then retype.
Ah, I see. That is the only way. You cannot, retext the contents.
Yeah, or I can
Yeah,
type.
you can type and
I can type.
Uh-huh.
So starting from who?
Let me see how many. We have 7 in total. Yeah, I think we can start from 1, 2, 3. Oh, we have only 6. Maybe you can start, and then each of us can answer one of them. We have 7 in total. There are 2 documents.
Okay,
yeah.
So I can start to, for example, first hydrohalogenation. So reagents, very simple, is HX. Just HX, just nothing else. And then syn or anti. Well, because it's a carbocation mechanism, basically the halogen can attack from either side of the carbocation. So it's both. And then regional specificity is obviously just M room. Okay, I'm good.
Good. I think Yang and I can answer any question you don't like.
Okay, who will be next?
You guys can pick up and
I'll do the next one because it's easy. So
yeah, you can just say.
This one is just X2. And it will be anti.
X2, anti, then
this one is the same because
this is just not applicable because both of the groups are the same. Just one note. Normally, we can only do chlorine and bromine. Well, like because fluorine is much too reactive. Fluorine will basically strip hydrogens off of the carbon. Sometimes we don't want this. And iodine is, well, not really reactive enough. So like halogenation is sometimes it's like we think it's only limited to chlorine and bromine.
This
But
is a
still.
very good point. When fluorine gas reacts with those alkenes, it might kind of completely substitute the hydrogens, in the compounds. So that is a different story. Not only kind of, break the pi bond and add to each side, but it might also substitute the hydrogens as well. And the reaction is very rigorous, so there might be an explosion.
Yeah, so don't touch fluorine gas, people. Fluorine gas is bad. Okay, who's next?
I can do the third one.
Yeah, go ahead.
It's X2 and water, I believe.
X2 and water. Or sometimes.
Or like ROH.
So what do they have in common? Water and ROH.
They have an OH group, right?
So what does the OH group do in organic chemistry?
More specifically, what is the function of the?
Yeah. What is the function of the OH group?
Is a solution? Like
it is a solvent. It is indeed the solvent. Either water and alcohol are both the solvent, but more importantly, it is involved in the reaction and act with a certain function in this specific reaction.
Think of arrow pushing.
Like, I'm not sure like what you are referring to though.
There is a nucleophile or electrophile.
It should be nucleophile.
Yes. So every single nucleophile can do this reaction, not just water or ROH.
How do you type this? Oh, it's just colon?
Just a colon.
Oh.
I
think it's anti. I think it's anti. Oh, I think it's follow IM rule. Yeah.
M rule obviously involves hydrogen. So there is no hydrogen in here. So how would you change M rule to how do you explain this?
So basically the nucleophile is added to whichever carbon that has more substitutes.
Okay. So nucleophile are more substituted carbon. Nice.
Oh, by the way, Jack, how did you kind of change the superscript, subscript, and the italic fonts?
On Windows, it's Control plus, and then it counts subscript, and Control Shift plus is superscript.
But it seems like your way is not you finish the typing and then you change it.
Yeah, for example, I can type
the
and then press it and then do other stuff and press it again.
Also, you kind of hold that two keys and then do the typing.
I mean, I can type with one hand. Typing, I can type with my left hand, and then I can press the keys with my left.
Okay, I got it. Okay, that is different from my usual way. I always kind of finish the typing and then further adjust the format. But this is cool.
Okay, what next? Who wants to do the next thing?
I will do this one.
Okay, go ahead.
Catalyzed hydrogenation. So you have hydrogen and this whatever cat.
Yeah, cat.
I think this should be sin.
Sin. Yeah, it is sin. It is sin. Well, obviously
I think
no
this makes sense here. Yeah, it's only
there's no regiospecificity because there are both hydrogens. Okay, so now it's an acidic cat.
So just acid and water, like protons and water.
Okay.
And like both.
Oh, nice.
And alcohol goes to the most substitute, so amyl.
Getting to the
Maybe I can
fun
take
part.
this one. So Yang Zhou, you will be the next. Okay. So the reagent is mercury acetate and acid.
Acid?
Acid. Acid is commonly used. Let me see. What might the function?
To neutralize the acetate that's produced.
Yeah, probably. To protonate the acetate, prevent the acetate to work as a nucleophile. Probably, but not very sure. But acid is commonly used, with the mercury, acetate. Although it might not be very, important here. So the second step.
That makes sense. That makes sense because like normally we see nucleophiles. I was just gonna write nucleophiles, but like if you brought it up, like the acetate ion. But I think the acetate ion is not such a great nucleophile.
Yeah, it's not. But in the second step, in the first step, we don't need to use the nucleophile, right? Because we want to stop at the Mercuranian step, right?
Like
remember the ring.
Yeah, on the in the first step, we actually go to this stuff. Like all of this is involved in oxymercuration.
I see. You're right. Mm-hmm.
Okay, so I'll just write nucleophile.
And it's commonly, just water because the mercury acetate is dissolved in water, right?
Yeah, just write RH.
The second step is sodium boron hydride, a strong reductance to remove the mercury and replace the mercury with hydrogen.
Okay.
Obviously, this is also anti because there is a three-membered ring. So this is the anti-Markov-Nikov because this is the Markov-Nikov. I'm thinking about the hydroboration.
I'll just add no rearrangement.
Very good point.
Last one, Young. Come on.
Yes, BH3CHF. And then H2O2 NaOH. Sin.
You feel your sins crawling
You
off
feel
your
your
back.
sins crawling on your back. You feel like you're going to have a bad time. Anti-M.
Okay, so that's everything we just learned in the past 3 periods. Looks like a lot, but it actually is a lot. Like
I agree with you. It's actually a lot, and especially the last 2 reactions, the names are even not so straightforward, right? Oxymercuration-demercuration, hydroboration-oxidation. I don't know. Probably it's a little bit, overwhelming in the beginning. It will take some time for you to fully digest those names, those reactions, those rules,